analysis of the application of stochastic gradient descent to detect network violations. Introduction. Machine learning as a sub-branch of artificial intelligence is actively developing in various areas of technology and human life. It is used in a number of computational problems in which the development and programming of explicit algorithms with good performance is difficult or impossible. Examples of its applications include email filtering, detecting network criminals or malicious insiders, optical character recognition, ranking training, and computer vision, and more. For so-called training, machine learning often uses statistical techniques and algorithms, one of which is the gradient descent method. However, when training the model, a huge sample of data is most often used, as a result of which the standard deterministic gradient descent does not show the best time result. A modification of deterministic gradient descent is stochastic gradient descent, which provides accelerated learning without significant loss of efficiency. The purpose of this work is to analyze and reveal the operation of stochastic gradient descent, analyze the application of this algorithm in the process of machine learning training, and compare it with deterministic algorithm. Review of the literature. The paper discusses first-order methods, namely methods that use the gradient of a function. In the author's work 3, the general optimization methods is the usual gradient descent. The author of 5 describes a formal description and description of the algorithm for solving the gradient descent method. In his work 5, the parameters are updated iteratively in the direction of the gradients of the objective function. Due to the high computational complexity in each iteration, stochastic gradient descent (HDD3) is proposed for a large amount of data. Therefore, the authors 8-10 propose an analysis of the application of this algorithm in the process of machine learning training, as well as its comparison with a deterministic algorithm. The result of using a simulation of the usual gradient descent described in 1.4.16, when the weight is updated only after viewing all the elements and the accuracy of the model becomes very low. It's described that with this approach, gradients are updated more accurately. In this paper, authors conduct a study with a large number of epochs, where gradient descent shows the best accuracy of training. Methods of solving. Gradient descent is a way to minimize an objective function j of theta that is parameterized through model parameters theta in R to the d power. By updating parameters in the opposite direction of the objective function delta with index theta, j of theta, gradient to parameters. The learning rate eta determines the size of the steps that need to be taken to reach the local minimum. When analyzing, you need to monitor the direction of inclination of the surface down, which is created by the objective function. Gradient descent. Gradient descent is an iterative first-order optimization algorithm in which steps are taken to find the local minimum of a function that are proportional to the opposite value of the gradient, to approximate the gradient of the function at the current point. Figure 1. Figure 1. Intuitive image of the gradient descent algorithm. Standard deterministic gradient descent. Deterministic refers to an algorithm that returns the same result each time, regardless of the number of iterands. A normal gradient descent is able to return the same values due to the fact that it's performed on the full amount of data that comes to its input. That is, it works with the same input data and also performs the same steps on it without any accidents, which gives the same result at the end. Stochastic gradient descent. Stochastic refers to an algorithm that returns different values each time, i.e., the algorithm contains a certain stochastic or random relationship. Different output values occur due to the fact the stochastic gradient descent is not performed on the entire volume of input data, but stochastically selects only a certain predefined number of records for each epoch. Such a set of individual records is called a batch. Application in machine learning. Gradient descent is widely used in machine learning. In fact, because it allows the model to learn from its mistakes and inaccuracies. When training the model, a loss or error function is introduced, which provides information about the difference between the result expected and returned by the model. Since we, of course, cannot change the input data from the dataset, we must optimize the coefficients of our model. The gradient of this function shows us how each coefficient affects the final error function. Applying a gradient descent to the loss function after this allows us to achieve the minimum of this function by adjusting the coefficients, i.e. make the error minimal. In this way, the configurer model allows us to use it for our tasks. Thus, it becomes clear that the gradient descent itself, stochastic and standard, is not used in machine learning. Its implementation occurs only as an auxiliary tool for minimizing loss or error function in machine learning algorithms. Experiments. Recognition by convolutional neural networks trained using stochastic gradient descent. Digital recognition is still a relevant topic today, which can be applied in various areas of our lives, starting from the recognition of bank card numbers in bank applications and ending with the recognition of mathematical expressions. As you know, convolutional neural networks are best suited for image recognition, which, unlike conventional deep neural networks, use convolutions to find patterns in images that allow for improved prediction. Convolutions also compress images, which significantly increases the speed of analysis. Convolutional neural network model. To implement a convolutional neural network, I chose the following architecture, a diagram of which can be seen in figure 3. Input 28 by 28 by 1. Convolutional layer 24 by 24 by 10. Max pooling 12 by 12 by 10. ReLU activation function. Convolution 8 by 8 by 20. Max pooling 4 by 4 by 20. Complete connection of 320 neurons. Complete connection of 50 neurons. Output for 10 classes, 10 digits. Note, there is a ReLU activation function between all full connection layers. ReLU of x is equal to the maximum between 0 and x. Figure 3. CNN diagram. Training and testing parameters. The data is randomly divided into 60,000 training images and 10,000 test images to prevent the possibility of retraining when the model shows good results in training, but then cannot distinguish samples that were not seen during training. As an optimizer for training, a stochastic gradient descent was chosen with the experimentally selected best learning rate. Learning rate equal 0.01. The training will last for 3 epochs, with a different number of images in each batch for the step of the stochastic gradient algorithm. The negative logarithmic likelihood function, L of y equal minus logarithm of y, is chosen as the loss function, which is simple but at the same time powerful in classification problems. Accuracy testing will reflect the ratio of the number of correctly predicted images to the total number of images in the dataset. Accuracy equal n of true over n multiplied by 100%. Work results. The graph shown in figure 4 shows the change in the value of the loss function relative to the number of elements seen during a pure stochastic gradient descent, 1 element per batch. At the same time, the accuracy of the neural network for 3 epochs was only 8%, which means that only about 800 out of 10,000 images were correctly identified by the network. The final error was about 4.2315. Figure 4. Graph of the ratio of the amount of losses relative to the number of elements passed by the network with a batch size of one element. CNN diagram. The graph shown in figure 5 shows the change in the value of the loss function relative to the number of elements, seen with a batch size of 64 elements. At the same time, the accuracy of the neural network for 3 epochs was 97%. The final error was about 0.327. Figure 5. Graph of the ratio of the amount of losses relative to the number of elements passed by the network with a batch size of 64 elements. The graph shown in figure 6 shows a change in the value of the loss function relative to the number of elements seen with a batch size of 128 elements. At the same time, the accuracy of the neural network for 3 epochs was 96%. The final error was about 0.421. Figure 6. Graph of the ratio of the amount of losses relative to the number of elements passed by the network with a batch size of 128 elements. The graph shown in figure 7 shows the change in the value of the loss function relative to the number of elements seen with a batch size of 256 elements. At the same time, the accuracy of the neural network for 3 epochs was 93%. The final error was about 0.686. Figure 7. Graph of the ratio of the amount of losses relative to the number of elements passed by the network with a batch size of 256 elements. Since there is no ready-made implementation of normal gradient descent among non-libraries, we can only stimulate it with stochastic gradient descent by setting the number of elements in the batch to 60,000, i.e., to update the algorithm weights, we will need to use 60,000 images. The graph shown in figure 8 shows the change in the value of the loss function relative to the number of elements seen during the stimulated normal gradient descent. At the same time, the accuracy of the neural network for 3 epochs was only 9%. The final margin of error was about 2.284. Figure 8. Graph of the ratio of the amount of losses relative to the number of elements passed by the network with a batch size of 60,000 elements. Simulation of a normal gradient descent. Discussion of results. In pure stochastic gradient descent, when we consider only one random element to change the weights, the loss function has the highest values of all. This is due to the fact that one random element is not enough to describe the trend of movement of the loss function and the corresponding gradients for all other weights. It can be seen that the value of the loss function is constantly moving up and down. Obviously, with this movement of the function, the accuracy of neural network predictions turned out to be very low, only 8%. When we use a MiniBatch, stochastic gradient descent for different number of elements in batch, 64 on 128 or 256, the value of the loss function also increases and decreases alternately, but in all cases it still moves to a minimum. The only difference with a different number of batch element is frequency of these movements, since the weights are updated with a different number of used elements. At the same time, MiniBatch SGD minimum. The only difference with a different number of batch element is frequency of these movements, since the weights are updated with a different number of used elements. At the same time, MiniBatch SGD showed the highest accuracy of predictions, which was 97% for a 64-element batch. As a result of using the normal gradient descent simulation, when the weights updates takes place only after viewing all the elements, we see that the value of the loss function also falls. But since the weights update is so rare, this movement is very slow, so the accuracy of the model also becomes very low. However, the gradients with this approach are updated more accurately. Presumably, with more epochs, gradient descent would show better training accuracy. Conclusion. Looking at the results of stochastic gradient descent and comparing them with the simulated normal gradient, we can see that HGD performs training much faster, because only 3 epochs are enough to achieve 97% accuracy with the correct number of elements in the batch. At the same 3 epochs, gradient descent was able to reduce the value of the loss function by several tenths. At the same time, pure GHS also shows poor accuracy results, since it cannot describe the change in weights using a single random element. Taking into account the previous thesis, we can conclude that the use of a MiniBatch stochastic gradient is more effective and more in demand, since it performs the fastest and best training of the model.